All right, here we go. We have a problem with a metal box on a wet table that is made out of wood, and it is being pulled down by a weight via a rope and pulley. And we're simply looking for how long it's going to take to reach the end of the table. How long it's going to take is affected by a few things. It's affected by the weight of the 5 kilogram mass. It's affected by how long it has to fall, or how long it has to slide, the 1.2 meters. It's also affected by the mass of itself. So let's look at the solution. All right, the system in this problem is the metal block. We have a resistance force of kinetic friction resisting to the right. We have a applied force pulling to the left. The difference of those two is going to be the net force, and the net force causes a mass times acceleration. So let's look at our givens here. We have the mass, let's call it the system, of the system is 3 kilograms. The mass of the, let's just call that a weight, is equal to 5 kilograms. We know the distance it needs to slide is 1.2 meters. Also, if you click the link, you should get a coefficient of kinetic friction equal to 0.20 for wood and wet metal. And I believe that's all we know. So, like always, we write up a net force equation. The net force equation is going to be the force of kinetic friction minus the applied force. All right, and which one's going to be bigger, the kinetic friction or the applied force? The applied force will be bigger if the box slides to the left. So, if the applied force is bigger than the kinetic friction force, we're going to get a negative number for the net force, because something smaller times minus something bigger gives you a negative number. So, let's start plugging stuff in. Okay, the net force is equal to ma, mass times acceleration. Kinetic friction force is going to be equal to the normal force. Let's think of this as boxes. Each one of these is a box, maybe a Christmas present with a nice ribbon on top. All right, let's open up each box. When you open up net force box, you have two things inside of it. It's like when you get a present and you have two presents inside. You have a mass times an acceleration. When you open up the kinetic friction box, you have force, which is a whole new present, times the coefficient of kinetic friction. Minus, the applied force really is the force of gravity on the 5 kilogram weight. So we're going to say minus the mass of the weight times the acceleration of gravity. Let's take it one step further, all symbolically. We have the mass of the system times the actual acceleration that it's going to have as it slides to the left, and equal the normal force. Okay, we have another box here. What is normal force equal to? Well, since this box is neither accelerating upwards or downwards, it's in uniform motion vertically, we know the normal force is going to equal the mass of the system times the gravity times the coefficient of kinetic friction minus mw, mass of the weight, times the acceleration of gravity. So, now that we have it all symbolically written out, we can plug stuff in. Really? And really, look at this. We have everything is known except for acceleration. It's pretty cool. So the mass of the system is 3 kilograms times an unknown acceleration equals the mass of the system, which is 3 kilograms, times the acceleration is 9.81 meters per second squared, times the coefficient of friction is 0.20, minus the mass of the weight is 5 kilograms, times positive 9.81 meters per second squared. And it's positive because I already counted for the negative right here. So now it's all just algebra, okay? Simply solving for the acceleration. All right, so 3 times 9.81 times 0.2 is equal to a frictional force of 5.9 newtons minus, okay, 5 times 9.81, and that gives you 49.05 newtons, and all that's going to equal 3 kilograms times acceleration. All right, so now we have, think about it, what does that 49.05 represent? It represents the applied force pulling to the left. That 5.9 newtons represents the kinetic friction resisting to the right. And when you subtract those together, 5.9 minus 49.05, you get out negative 43.15 newtons. That number represents the net force. And the net force always equals the mass of the system times the acceleration of the system. So you take 43.15 newtons divided by 3. You get an acceleration of 14.4. Of course, I'm rounding up a bit here, which is fine. Meters per second squared. So there's the acceleration. But in this problem, we're looking for the time. We're looking for how long it takes. So again, we need to go back to the last chapter to solve this problem. We have the acceleration, we have the distance, we're looking for the time. Very simple. We use this equation. 1/2 AT squared plus V0 times T. Now, again, we can assume the initial velocity is 0. We can then solve for T. We can bring the 2 to the other side. Bring the A underneath equals T squared. So we square both sides. Then you just plug stuff in. Square root of 2 times 1.2 meters divided by an acceleration of 14.4 meters per second squared. And that ends up being, give me a second here, the square root of 1.66, which is 0.41 seconds. 0.41 seconds equals the time. And there you have it. My wife wants to say hi.
Hey, y'all.